Okay, so I'm so intimidated by Alexei's question. Maybe I just go for a walk.
It was an auto question. I was asking myself, trying to. Okay. I don't know the answer, unfortunately.
So my talk is supposed to be a follow-up of what Andrea started off in the afternoon, and I will try to do my best to give you a quick review on the TMD phenomenology of polarized TMDs. Now, if the question is, where can we learn about TMDs? Then the answer is more or less anywhere in the globe. But if the question is, including EIC, mind you, I put it here, somewhere in between. If the question is, which experiment do we need to learn about TMDs, then mainly we have 3 experiments, and they were discussed very nicely and in a very sort of in-depth way this morning. We have Drellian processes in which we learn about the distribution functions. Distribution functions are somehow embedding information on the confinement, so how matter holds together, how quarks and gluons are actually linked to form the visible matter, or the proton if you want. On the other side, we have the plus and minus, which give clear and clean information about the fragmentation functions. And fragmentation functions are more related to hadronization. So the mechanism, which is a more dynamical mechanism, in which quarks and gluons, which are produced in elementary scattering, are combining together to make hadrons and therefore visible matter. In between, there's semi-inclusive deep inelastic scattering, in which the cross-section is actually a convolution of both distribution functions and fragmentation functions. So in semi-inclusive deep inelastic scattering, we have a lot of information, but this information is more tangled in a way, and it's, you require some expertise to be able to disentangle the 2 contributions in these processes. This morning, Elke said something which made me think. So she said, we have to be really brave, and we have to be good enough to be able to test universality by using different experiments. And this is clearly very important. And to me, EIC is one of the most important steps toward this, because it's linking, as far as Sivers is concerned, it's linking experiments like HERA with extremely large Q-squared and energies and very low X also, to experiments which are on the other side on the other end of the universe, in a way, because it's low Q-squared and low Q-squared and quite and rather large X. And in between, EIC is where EIC is sitting, and it can actually connect these 2 different worlds. But we also have to learn, and this is something that we discussed later on and in the afternoon with Andrea, we also have to learn not only how to describe different experiments, but also how to use physics in different kinematics regime, mainly and starting from the scale Q, right, of the energy of the experiment. And we have seen that some of these observable cannot just simply be extracted in some experiment at very large Q, for example, or very large energy, and then expect that they work perfectly well in other experiments which are covering different kinematics regimes. This is not to be taken for granted. In my talk, I will focus mainly on Sivers processes, and as I said, Sivers is now measured in a number of experiments, but hopefully in the future we will have this new facility which will help us a lot understanding many things. And the main thing that this new facility will do is to extend both the X and the Q-squared coverage that we presently have now to bridge some of the unknown regions that are still there. It will also, and I actually have stolen this nice picture from Elke's talk at SPIN 2016. It will also help us to disentangle, for example, valence and C contributions as far as the PDFs are concerned. Now, many of the speakers of today have already shown you that if you become transverse momentum dependent, transverse momentum sensitive, your distribution function, which in the collinear approximation are 3 functions, different functions, become 8 functions. While the fragmentation, in the fragmentation realm, if you stick to spinless hadrons in the final state, you only have 2 relevant objects. One is the unpolarized fragmentation function, and the other one is the Collins function. And I will stick to that. In today's talk, I will basically talk about the Sivers function and the Collins function. Now, let's start from Sivers. The Sivers distribution function is embedding the correlation between the proton spin and the quark transverse momentum. And it's one of the most studied and perhaps the best known of the polarized TMDs nowadays. It can be studied in Drellian proton-proton or hadron-hadron scattering, and also in semi-inclusive DIS. It has some factorization, some universality properties, which are not totally trivial, because it's sensitive to the way the initial and final state interaction behave in the processes. So it has some degree of process dependence. And we now know that, well, it's a prediction that the Sivers function should reverse its sign when it's measured in CDs compared to what to the sign that it has when it's measured in Drellian processes. And we have a few hints of this sign change of the Sivers function from experimental measurement, one from the STAR collaboration, which has measured the Sivers function in polarized proton-proton scattering with W and Z production, and also by the COMPASS collaboration, who has last year, quite recently, measured the Sivers effect in the Drellian process that they had, which is a proton-pion scattering in their case. And they've also made a reanalysis of the CDS data on the Sivers effect using bin, multi-dimensional binning, and studying them on a binning in 4 Q-squared bins, which make, well, at least the intention was to make the Q-squared evolution study a bit easier for this data. So what we have done until a few months ago was to go over a new study of the Sivers effect and a new phenomenological analysis of these new data. This is the model that we used in the past, and let me just draw your attention on the fact that in the past for the Sivers function, we used an X dependence, which was coming from the unpolarized collinear Parson distribution function, PDFs. So the Sivers function was parameterized in this way, where this function was simply a Gaussian multiplied by the collinear PDF, while the K dependence was all factored out into these Gaussian parts. Now, this was more or less the only option we had when the experimental information was scarce. And so we had to start from something, otherwise the data wouldn't allow us to make a phenomenological, reliable extraction. But now, the number and the quality of the data allow for a different parameterization, which does away with the unpolarized PDF, the collinear unpolarized PDF, and we can have this factorized form. It's still like a Gaussian in K-pair multiplied by a functional form for the X dependence, but there's no PDF input anymore. This parameterization in perspective, it's easier because rephrasing everything in terms of the momentum is better suited for the study of TMD evolution. And also it makes the expression of the actual symmetry, which is what you minimize in your analysis, much simpler.
And I think that I think what you mean to say here is that at the time there was no information about the counterpart of Sivers function in the collinear regime.
Mm-hmm.
Or better say, well, we didn't parameterize it this way. While now, as far as we are pretty sure that the counterpart of Sivers function in the collinear limit is true-stirring matrix element, which is not actually known quite well, then you have to parameterize it directly in this particular extraction. That's why this prefactor.
I mean, this is still one possibility, but it's a possibility which can help us also in the connection with other kind of studies or approaches like
What's the other possibility of thinking?
Well, we basically investigated two possibilities. One was using the TMD scheme in a very simplified form, and the other was this three evolution scheme. So this is what we actually have done. But I'll show you.
Okay.
Okay. So apart from this, which is just the technology, before starting, we observed the data, and we already knew that there were some problems. One of the problems is that when you try to fit different experiments, you first of all have to see whether the data are fully consistent or whether there's some tension. And in this case, it's been known for quite a while that there is some tension for the Sivers effect when you compare Compass and Hermes results. On the other hand, these two experiments span different ranges in Q-squared, and they have also different average Q-squared values. And this can be crucial. So maybe this can be a signal of possible TMD evolution effect, or maybe it's just a kinematic effect or something else. Yeah. But anyway, we have to take these into account. So we made a very simple test, and we fitted Hermes and Compass data on the Sivers asymmetry separately, right? With a very small number of parameters. This is a very crude fit, only taking pi+ data. But if you make independent fits, you see that the two experiments populate two different regions in the parameter space. Okay, so they are very unhappy to have the same totally equivalent fit. Suggest you that the free parameters that you use for the model are different in the two cases. And if you attempt to fit all the data together, what do you think it happens? That your min goes and sits in the middle, okay? And so it tries to compromise for the value of these two parameters. But we were not happy about it because we don't want to push a large number of data all together and then just try to adjust the parameters or maybe use more refined models with a larger number of parameters.
So that happens all the time with unpolarized PDF fits, because also there, the Hera data and the telephone data and the LHC data cover completely different XQ-square regimes. And it works. So why doesn't it work?
Yeah, first of all, you have to make sure that the difference in Q-squared is significant. In that case, it is. Here, the difference is very small. So we were not really totally happy about this net separation between the two. But also, in this case, these are asymmetries. And if you give me a minute, I'll tell you exactly what happens.
Perfect.
So, and maybe I just thought for that. Okay, so what we're fitting here are asymmetries, and asymmetries are always ratios. To make asymmetries, you take the ratio of the difference of polarization up and down, and you weight it with the sum. And the sum is the unpolarized cross-section. So our first question was, are we actually getting the right cross-section? Are we describing satisfactorily the cross-sections for the two experiments? And the answer is no, and we knew that because in the past, we attempted to fit the multiplicity data for Hermes and for Compass with our very simple model, totally trivial. And actually, we got good results when we fitted them separately, but we never managed to find to fit them simultaneously. Okay, so they require different values for the two free parameters that we were using. So we knew that there was something wrong really on the foundation of the whole building. So the conclusion is simple models seem to work well, but cannot describe both this set of data, both these two experiments simultaneously. However, if you reproduce your cross-sections well for the two experiments separately, and you use those in the denominators of your asymmetries, then the asymmetries become completely consistent. And your fit, you see, the two independent fit are nicely overlapping in a region, which is exactly the region where the simultaneous fit goes and sits. Okay? So in this way, we of course, I'm not saying that we understood why things are not working well, but we just took care of it. And we made sure that our fit was a consistent one. Now, what is surprising, and let me go back to the talks of Andrea and other people's work, is that while simple models seem to work well, at least separately, more refined calculation seem to be giving even more difficulties. And in Andrea's talk, we've seen that although the shape in the transversal momentum space is well described when you do a global fitting, there is a very serious problem with normalization, which basically has to be fixed by hand, bin by bin. There is also, there was all the work related to order alpha squared calculation of the Sivers cross-section in the past. And large K factors were found. These are data from HERA, so they are very high Q squared kinematics. And they are also PT dependent. K factors are not just constant numbers, they depend on PT, and they are strongly affected by the cuts that you use in the kinematics. This, in a way, was studied again and in a more refined way with new data from Compass very recently by Nobuo Sato, Ted Rogers, and Osvaldo Gonzalez and Wang, and they actually find that there are large discrepancies even when you go to order alpha squared calculations between the data and the calculation you do. And their conclusion is that these problems might be generated by the collinear PDFs and fragmentation function. So there is actually a problem which is connected to, I take the result of well data fits for the PDFs, which are driven by some data, maybe very high energy or different kinematics regime. I drag it to a different kinematics, and maybe they don't work anymore. Maybe when you get to that stage, they are not appropriate anymore. So this is a problem that we really have to face, and certainly IRC will help us.
Although it has to be said that the large K factor you just reported suggests otherwise, right? I mean, this might be part of the puzzle, but you know,
yeah, exactly.
If there's a K factor of 10, right? And it's just
this is the conclusions I've copied from their paper, but of course, I mean, maybe this is also even the most important of the effects, but certainly there are other things.
Was it leading or next to leading order? Comparison. So it's comparison with
next to leading order. It's alpha S squared.
Next to
leading. And it's only high to D. Okay. Now this is not the topic of my talk. I want to stick to polarized, but before we can do any reliable fit of the Sivers or any polarized stuff, which is basically based on asymmetries, we have to make sure that we know how to compute the unpolarized cross sections. Otherwise, there's nothing we can really do, and whatever we do is just a fix. It's not anything we can really rely on. Okay, so to answer Ignazio's question this morning, when you do the fit, you find that the Sivers U contribution is well constrained. Then for the D, you don't find a very strong constraint because you have to decide what you do. So you know more or less what the U wants to do, but then you have to play with the D contribution together with U bar and D bar at least, okay? And we find that the data as they are now are not actually constraining D very well, so much so that if you make a fit using U and D, or a fit using U and U bar, you find very, very soon like chi-squared. So the fit needs one more contribution. But whether this is D or D bar or U bar, the data don't tell you, right? So D is poorly constrained, and the Sivers is Sivers C is basically unconstrained. And again, this is something that EIC can really teach us about. Okay, so in this study, well, when I'm saying that the D contribution is unconstrained, I'm saying that.
I'm saying it can have whatever sign. While the statement of this morning was it has a minus sign in respect to
it does if you only put U and D. Then to lower down your asymmetry, you need a negative contribution. If you put D and a little bit of C, then the C can do it itself, and you don't need any D anymore, right?
You need a large C.
You need
a very large.
Not a very large C. You need a consistent C.
At least for long as you have much more deep parts and deep bar in the proton asymmetries are large. So you would need a very large asymmetry for U bar.
You would still get a very good fit. So the data are unable to distinguish, right? Then you can put your own prejudice. But
not enough.
Not enough. Okay, good.
That's what I said. So if you want to take over the role of the D bar, the U bar must have a large.
I misunderstood you. I said you said a lot.
No,
not enough. Okay.
When you say that the U bar could be enough, you did not. This is the result without the positivity bound implemented.
But the positivity bound for the Sivers is never a problem.
Even when the U bar is so big.
No.
So actually, can I ask
okay.
why are you so surprised that the D bar is opposite sign? Basically, in most of the polarized, also for the simplicity, they are oppositely polarized.
Yeah, polarized, yes, because the cross-sections are always
what does that mean? How can it be opposite sign in the That would be a negative PDF.
And
And then a low, yeah, okay, fine.
No, come on.
Make it straight, yeah?
Can I suggest
So negative numbers.
I forgot the
Yes.
Sorry, let's postpone the discussion.
Okay. So I don't want to go into the details of this fit, but anyway, we worked really carefully and we started with a reference fit, which is a very simple one in which we basically have only valence contribution, or if you want, it's the sum of valence and C, but we don't distinguish. And for this case, the fit is a perfect one. It's the one that you would use when you teach your students how to use mean, okay? So you have a very nice parabolic shape, quadratic profile for the chi-square, and when you test for the parameter correlations, you get this nice egg shape.
It's not clearly
plot.
it's huge.
No, this is not supposed to be parabolic. I mean, it's a parabola. It's parabola if you look at it above. But then we were not happy about this fit because the uncertainty was, sorry, I'm messing up. The uncertainties were not evaluated reliably. So we also tested another configuration in which we allowed for some C contribution. And we wanted to study how the low X uncertainties would change. And we were quite surprised because by comparing these two different fits, we found out that the chi-square doesn't change, doesn't improve at all, even if you add more parameters. But what happens is that your nice parabolic quadratic shapes are totally screwed up in these new parameters, and there's a very, very strong correlations between the new parameters. And this tells you that you have to stop because you are overfitting. You are putting in parameters that your minimizer doesn't know what to do with. So we are not giving to this particular fit any physical importance. We only use it for the uncertainty. I hope you can see the colors. Here, the blue bands are the uncertainty on the Sivers function in the simple fit with only valence, basically. And the gray band is the uncertainty. The central line doesn't change, but the gray band is the uncertainty when you also allow for the C contribution. And as you see in the low X, where there are no data, your band becomes much larger, it's much more reliable. This blue band here at low X, where you have no experimental information, doesn't make any sense. And I want to show you this on the data, because this is perfect.
Go back to the previous slide. But here, so the right-hand side is the D quarks, right?
This one is, in our notation, the change as well. The signs of swap. So U is positive and D is negative.
I don't mind, but so right-hand side is the D quarks, and
yes.
So you see here that at least above, what is it, 0.003 or so, the D quark Sivers is actually very defined, right? Okay,
Okay.
maybe not perfect, but I mean,
No,
it's clearly non-zero and it's negative, right?
No. So what I did before was I started with only one flavor. I don't even call it UD or whatever. And I get out a function which is clearly positive. So the data are telling me if you only have one flavor, that flavor has to be large and positive. Then I put in two flavors, and I don't call them again. So one is U, okay? And the other one can be D or D bar or U bar or whatever you want, a combination of them. At that stage, I'm already seeing that that contribution is not well determined. In here, I'm already putting in my prejudice because I'm fitting by putting in U and D. And I say there are two contributions, one is U and one is D. But I don't know whether it's D or something else.
But you already did it for the U.
Sorry?
Because I don't know if you really allow the D bar or the U bar to be very large. I bet that you could also describe.
Yeah, but then allow me to put in my prejudice and say this is not U bar, it's U. Okay. Yeah. Because I know that these data are U dominated. I mean, this is common knowledge. It's not. It's something more than a prejudice. But when it comes to separating U and D, that what I'm saying to you is I'm not sure whether I'm able to separate U and D, and that this D is really the D alone, not maybe a combination of many other things.
It's the same question as I have used, of course. I said that the valence structure is dominant. Therefore, I say, okay, the canceling piece is a valence quark and not a C quark.
Yeah.
If I say, okay, I put it out of the window, I can also not say that the U quark has to be the dominant piece. I can also say it's just everything is a C quark and we generate it, and you cannot say actually from the bit if I put U and T is 0 and I just say, okay, U bar and U bar are allowed to be large.
You have to keep the balance between what you believe is true and what you try to get out from your field, right? So we've been really careful, and we said we're really sure about the U contribution, but about how to separate D and the C is not, we are unable unless we put in some of what we believe. And actually, this is what we did, because in here we had U and D.
Why would you believe that the U bar would be big and not D? But you would.
No. I'm not saying that I'm believing.
No, but then,
I'm just saying that the data do not exclude these with enough confidence. Okay. My chi-square doesn't tell me that.
But also then, in that case, the U is not going to be large. It could be a D bar. No.
Because there are the
because your data is dominated by your work. Your data is dominated by your work.
But if the U cross Sivers is 0, if I set it to 0,
yeah,
the U, I mean, the Sivers symmetries are not that huge, so they are 5%. If you just have a very large C polarization, that's what all the time.
I'll try.
I try. You can even
I would be surprised if it worked. I think it would.
I bet you cannot fulfill the positivity bound
No, that's
because the U bar is so small at high X. Most of the data sets are impossible.
But
let's continue. And we have time for discussion also at the end of the afternoon session, so maybe we can go back to this.
Okay, so I just wanted to show you on the data how these things look like. If you rely on the blue bands, you see that at small x, you're doing really badly. So the way you estimate your uncertainty is very crudely underestimated. Whereas if you use the other fitting, then you have a much more reliable idea of what the uncertainty on your instruction is.
Could you explain why? I mean, all the error bars actually are actually still hitting the center line.
Sorry.
I mean, all the error bars actually are hitting the center line. So I don't see any problem there.
Look at the blue, maybe you don't see it well, but the blue uncertainty here is very, very tiny. And the blue uncertainty is you don't expect that when you go to the further region where you have the less number of data, here statistics is very clear, right? So you don't expect from a reliable extraction of your function, you expect your errors there, your uncertainty there to be rather large. And the fact that it's small is just because you're putting in too much of your prejudice into your initial parameterization. You have too few parameters, and you're unable to account for the uncertainty.
Bias.
It's called bias.
Yes.
It's called bias. Okay.
Actually, there was a dedicated talk last week. We discussed quite a bit what kind of bias we prefer if we fit parameterization to some rigid form. It turns out that the whole field behind this thing.
We should It's important.
So I'm more or less halfway. What do you want?
Oh my gosh.
Okay, so I'm not going to tell you about the TMD evolution. Maybe somebody will talk about this. We tested for evolution. We used two different schemes. One is the collinear twist-tree formalism. We use this expression, which is known. We took it from one of the expert paper, but neglecting the non-diagonal terms, which are unknown. And the other one is the TMD evolution from suggested from this bunch of people. And in both cases, we didn't use the full scheme, which is quite difficult and heavy to apply, also because in this case, for example, for the Sivers function, you need an input function, which is universal, but it's unknown. So we are unable to do this in a quick way at the moment. And so we use this proxy. And what we found out is that while in the collinear twist-tree evolution, there is quite a good distinction between the lines calculated at different q-squared. You can see the difference, you can tell the difference here. And the continuous line, which is here in the middle, is the reference fit, so the fit without any evolution. For the TMD case, now let me just say that here the evolution proceeds only through x. There's no intrinsic transverse momentum in this picture. In here, instead, you can hardly tell the difference between different values of q-squared. So the data at present are unable to distinguish between, between these different q-squared values. Although Compass made an attempt to separate them in 4 q-square bins, according to this model, the sensitivity is TMD evolution is very little. Okay, we will have more talks on maybe on the Sivers function. There has been a lot of work ever since. This is by no means a complete screening of the available papers and literature, but I think we will listen to some more details in the next few days. For the Collins function, we had a lot of discussion this morning. Rather recent data are now available, and Babar has made some measurement which, for the first time, are actually detecting the intrinsic, the caper of the Collins function in the Collins asymmetries in E plus E minus. However, also in this case, the difference between TMD evolution and a naive TMD or no TMD evolution, if you want, is very, very feeble. And if you compare these two studies with which one, they are two independent fits. One done with the TMD evolution formalism and the other done without it. You see that the description of the data is basically of the same quality, and this also works for for all of the asymmetries, and also in the comparison of the Babar data to the best 3 data, in which the gap between the value of q-squared is really large, because Bell is at q-squared of around 100, whereas Bess is around 3. So no strong signal of TMD evolution in the Collins functions as well. There is much more recent work about these in a different realm. For example, in jets, fragmentation. It's a recent paper by Kang and Alexei, Jumbo, Alexei, and Ringer, shows that data cannot resolve calculation done with or without TMD evolution. There are other ways to study this mechanism. One is the collinear twist-tree formalism, on which we will probably hear more in the next few days, or study a related phenomenon, which is dihedral production, and from which you can also cross-check for transversity. on all of these cases, EIC will give very important contributions. So I think we can stop. No, you're not allowed any.
We had a long discussion already, but let's get these two questions and that's it. So,
one thing in your fits, the intrinsic transverse momentum dependence, those fits were not yet X and Z dependent, right? Or at least not apart from this implicit one, Z dependence.
No.
There was no X and Z dependence. Right?
We found that to do that, we needed a number of parameters, which was really too much for the information contained in the data. So for as far as these data are concerned, you cannot distinguish. You throw in a very large number of pre-parameters and minimize it.
So that could have also very large.
The spirit of this work was really making an assessment of how far you could do by using just the experimental information and putting in as little bias, I learned, as little bias as possible. So the idea was to try and use minimal input to get out as much as possible from the experiment.
Yeah, but isn't that already a bias if you don't take any X and Z dependence into account?
Well,
I mean, that's kind of the same as if you kind of fix your functional form. It's also a bias.
It's just about fixing the Gaussian width. And you showed this morning the range in which the Gaussian width of your data is varying is between 0.2 and 0.3. So this is already smaller than the experimental uncertainty.
Well, I didn't show any data on that.
So
the point is, it will certainly actually have some X or Z dependence.
Yeah, I'm not saying that there is no Z dependence. I'm just saying that the Sivers asymmetries, as measured in cities processes, for as much as they are now, are not containing enough information to extract the shape of this Z dependence. Okay, so I'm not saying that it's not there. I'm personally convinced that it is there. I'm just saying that particular sets of data do not contain this information. And maybe if we make global fit and do more analysis and more data, then we can fix this better. I think the groups that are using the Z dependence and the X dependence for the K clip, they take it from a Monte Carlo which was prepared for the analysis of the Hermes data. Am I right?
No. I mean, it depends on if you mean with all the fits on the Sivers function, yes, but of course the new unpolarized fits are coming from the data. The unpolarized.
So you fit there are three parameters that you fit in.
They're given by the data, but the unpolarized data.
But in that case, they have about 8,000 data points. In this case, we have 220.
To fix that dependence, you need the unpolarized data.
So,
but that's
okay.
Do you see why? I'm
No,
just speaking.
I was thinking you tried to do them both at the same time, the unpolarized and the Sivers.
Absolutely not.
Daniel, who I'm going to cut your.
I was just a bit confused about this distinction between collinear twist 3 evolution and TMD evolution. I mean, TMD evolution with Sivers function, the OP piece has the choose term function in it, which evolves in the collinear twist 3.
No. I didn't. There's no connection to me for this. The way I'm using them, they're two independent models. Okay, so I'm not trying to use them at the same time or make any interpretation about what is what. I'm just using two different schemes. I try one, leave it there, and then I try the other.
But what is the TMD evolution scheme?
It's there's basically the CSS2 scheme.
Yeah, you just have an input Sivers function.
You have an input Sivers function, which is a phenomenological thing that you have to invent. Sorry. This one.
But we know what that input function is. Why not do it with OPE, and then you have your collinear.
Yeah, no, but you.
Sturman function. The collinear part of your Sivers function is the Sturman function.
Maybe, but here I didn't want to use it as an input. So to me, this is an unknown function.
Well, it's not. It's been derived. We
No,
know the OPE of the Sivers function.
Okay, so in theory, there is this connection, but I don't want to use it. Okay, I just want to start from scratch. In both cases.
Defer it to discussion. Actually, I think this is an important point.
That's an important point, but I have had a discussion.
I just wanted to say that Ted and John wrote this answers this. Ted and John wrote a paper where they said there's the OPE approach and there's this approach. To have an input function if you do it at the scale, not
Okay, so let's first of all thank Elena again. I think we can come back at 4. Is that what we're looking? 4, yeah, because this was supposed to be 10 to 4, but let's come back at whatever.
Let me unplug it, everybody.
4 sharp.